few just vocabulary to be familiar with. So when things bond, okay, things can bond one time covalently. Now keep in mind, covalent is the shared relationship. So this chlorine has 7, this chlorine has 7. They both want 8 in the end. So this one says, hey, I'll share one with you, you share one with me, and we can be a happy family. Okay? Now keep in mind, the electrons between now belong to both. Okay, they are shared between. Now we talked about with the polar bears and penguins, it's not always equal sharing, but if it's covalent, it is still shared. They are their children between them. Okay, now there's 2 ways we can represent these shared electrons. One way is you can put 2 dots between, or the other way is you draw a line that represents the 2 dots. The way I'm going to show you today, because it's my preferred method, is using the lines, but it is allowed to put dots between if you like that instead. Now, you can also form what are called double bonds, right? Where this one says, well, I need 2 more and you need 2 more. And so they both throw an electron in. So keep in mind that a line represents 2. So in a sense, a double bond actually represents 4 shared electrons total. But they belong to both. You can also form things called triple bonds, where they share up to 6 electrons between them. But there is actually no such thing as a quadruple bond. It doesn't exist. Any ideas of why not?
Too much negative charge and too much sharing?
Yeah, too much sharing, right? So it kind of goes back to actually those graphs we looked at last time, where if every time you bond, it pulls the atoms closer together, and closer and closer. And quadruple bonds are just too close, the atoms break. At least every time scientists have tried to make quadruple bonds stick, it just doesn't happen. So triple is the biggest that it goes to, okay? Now the length of the bond, like I said, will decrease the more times you bond, because the overlap is increasing. So single bonds are the longest, and triple bonds are the shortest. Same thing with stability, okay? Double bonds are a lot more stable, right? They would have a much lower drop than a single bond. Right, so they would be farther this way and also lower that way. And then triple bonds, right, are going to be stronger, but then also the shortest. Okay, questions on that so far? Okay, now we're going to take, and I thought I took it out, but you know, things just don't work out. That whole next section that talks about like rules, just cross it off.
Oh, okay.
I'm going to take a different approach, and I did this last year too, and it works the best. And it might be slightly different than how you learn in general chemistry, unless you were like Cooper L, because you had me as a teacher. Because other teachers teach it slightly different. Yeah, we're just going to skip the rules and just do examples. Okay, so I'm going to write our own set of rules for drawing image structures. Okay? All right, step 1 is determine the central atom.
I didn't even mean it was in it.
And draw what we call the skeleton. Okay, so step 1 is we're going to find the central atom, so which one's going to go in the middle, and then we're going to draw what is the skeleton structure, meaning where are they going to be placed, the other ones. Now, the simple rules for finding this central atom is the first thing is it's typically the single atom in the group. So for example, in this molecule of PCl3, P is our single atom, so P is going to go in the center. Okay? So I'm going to have P in the center, and then I need to put the chlorines around it. Now where you put the chlorines really doesn't matter. Typically, if we can, we keep things in a perpendicular type idea, so left, right, top, or bottom. But where is your preference? So I'm going to go 1 chlorine here, here, and there. Once again, if you want to put a chlorine on the top instead of on the side, that doesn't matter. Okay. If by chance, because we'll see this later, if by chance you can't identify or there's more than one single atom, then you go off electronegativity. Okay, so the lowest electronegativity will go in the middle. And we'll see that on the next problem. But valence electrons. Okay, so they're all coming to a party and they have valence electrons to share. So show what they have. Okay, so now last time we talked about how to find valence electrons. Let's see if you remember. So for a smiley face, so don't say it out loud. Show me on your fingers, but keep it like close to your body so other people can't see. How many valence electrons does phosphorus come to the party with? Good. If you're not looking at the periodic table, that will help you. Okay, you're showing me 5 on a smiley face. So to remind us, we count the columns, but we skip the D block. So 1, 2, 3, 4, 5.
How does the D block feel about this?
They feel good.
They don't feel because they're
Okay, so the 5 dots
Doesn't get rights.
around your phosphorus.
get no rights.
You don't get them rights.
Okay. Alright, now this one should, hopefully those I got it wrong will now know what to do. Show me on your fingers how many valence electrons does chlorine come to the party with? If you're showing me 7.
That's not how I showed 7.
Yeah, I was like,
Wait,
You showed 7
shoot.
binary.
Or
What
sign
if-
language.
what if you thought it was-
Why would you?
What if you thought it was 7 and then you just processed that your thumb was out and it made it an 8?
You were thinking 7 on your You just can't count your fingers. Okay, so now put 7 dots.
That was
Have you ever seen the sea cucumber? They're pretty nice.
7 dots for each of the chlorines.
Like a water gun.
Oh my gosh, I'm so excited for you to work.
Pretty cool. Do you want to become a sea cucumber?
Okay. Step 3 is we are going to bond to complete octets.
What did you do?
Okay, so we're going to bond to complete the octets of outside atoms. We're going to find that the central atom can do some interesting things, but the outside ones always want to bond if they can to get that full shell. Now I put octet in quotation because there's one atom on the periodic table that doesn't need 8 to be full.
Helium.
Okay, I guess 2 technically.
Helium and hydrogen.
Helium never bonds, but hydrogen would only ever bond once, right? Because hydrogen only needs 2 because the inner shell only holds 2. So what we're going to do now to share, remember it's like I share with you, you share with me. So connect 2 dots and turn into a line. Okay? Now, once you bond once, check your octet. Okay? So chlorine now has 2, because the line counts as 2, 2, 4, 6, 8. He's happy. How many means you're done?
Is that a smiley face?
Wait, is that a smiley face?
Tell me.
Yeah.
Okay, this chlorine has 2, 4, 6, 8. He's also happy.
Who's happy? Wait, is it?
I've got
That's
two
another one,
smiley
boy.
faces to me.
It's another one. Okay, 2, 4, 6, 8.
Happy.
Happy? Okay, you can check the center one to see where he's at.
We should check it.
4, 6,
I
8.
need that extra credit.
He's happy?
There we go. Yeah.
If everyone's happy, then you're probably done
There we
with
go.
that transition.
So we're happy too.
Yeah, like, nothing else.
So everybody's happy?
Yo!
Okay. Yeah.
Oh, those are my smiley faces? Gotcha.
Okay, question.
So if you ever accidentally draw a smiley face, you can count it as a smiley face.
Would I ever ask?
I mean, what if you like? I mean, like, if you turn on your side, HCl kind of looks like.
I was like, why is everybody laughing? And then I was like, oh. It's like someone with sunglasses on or something.
Okay, let's do it again.
Again?
Turn your focus back in front here, everybody. More happiness to come. Okay? Okay, so new molecule here, we're doing for HCN. So step one is we gotta figure out who goes in the middle. Okay? Now, there's one other thing with those central atoms. So they're all single, there's only one of each. So we have HC or N. One of them can never go in the middle. Yeah, hydrogen never can go in the middle, he's too small. Right? He only wants to bond one anyways. Okay, so then between carbon and nitrogen, and yes, carbon's going to go in the middle because it has a lower electronegativity. So I'm going to have carbon here, nitrogen here, hydrogen there. I'm going to spread them out a lot, but we'll get the gist. Okay, so step one, find your central atom and draw the skeleton. Step two, place the valence electrons of how many they come to the party with. So hydrogen comes with
No.
1, carbon comes with
5.
4. And nitrogen comes with 5. Okay, so start by just giving them what they have. So you kind of do it similar to like electron configurations where like 1, 2, 3, 4, and then you start pairing them up. I kind of take my first drawing as like a rough draft, and then sometimes I'll write a cleaner version once I'm done. Because if I like draw long lines and things, but so it really doesn't matter in the beginning. But okay, next two is we're gonna bond to complete the octets of the outside atoms. So hydrogen, draw a bond. I'm gonna draw a bond on that side. Okay. Hydrogen
Is happy.
Is happy.
I like
only
this
needs
lesson.
2, right? Okay. Now going to the other outside atom is nitrogen happy.
No.
Not yet, right? Because it has 2, 4, 6, and it wants.
Oh, I wish it was happy. You have to make him happy.
So to make him happy, Milo sees where we're going. We're gonna triple bond.
Okay, best.
Because once again, each line counts as 2. So 2, 4, 6, 8 is nice and happy.
Yeah.
Oh yeah, he is happy.
Wait, is carbon happy? Is he happy?
Carbon is happy.
Yes.
Carbon looks pretty happy.
8.
Look at that happy.
Which means we're happy too. Now, just FYI, so if this was, because that's fine, like that can be your answer. Often I'll clean up my final picture really quick, and I would write it like this. Because it's just a cleaner look at it. Once again, on the homework, I don't really care. Maybe FRQ, make it just a little cleaner where that triple bond is. And the more you do these, like the faster, and like you'll start seeing Aiden kind of like where you want to put the electrons, because you'll know where they're going to go. But Aiden.
So on the examples in the front, it shows like the ones that aren't connected still as like lines.
So it's
Like on
all.
the right of like nitrogen and also like the color.
Yeah, so it is acceptable to do lines for all pairs.
You don't have
My preference is to do lines for shared pairs, dots for lone pairs. Because next time what we're gonna do is gonna take these 2D pictures and turn them into 3D pictures. And so having a distinction between lines and dots can be helpful there, but it is like universally accepted to put lines instead if you want to. So, good observation.
I'll be at the exam, can we do the dots?
Yes. Yeah. Yeah. Either way, like they would know. This is just how I always do it. I'd say it's the most common way to do lines for the shared, dots for the non-shared. But, Trevor.
Yeah, I just have to say it because I've thought of it every time he's talked. But doesn't Aiden sound like Sulfur?
Like his voice?
Yeah, whenever he talks, I think I'm like, no, Aiden.
How does this relate to chemistry?
I just have to say it because you understand it.
I'm gonna have to listen now because I haven't had that thought.
I don't know. Maybe I'm weird, but it's every time.
You have a doppelganger of a voice of someone else. Okay, questions so far? Okay, let's do the next one. Okay, so
Is that
Okay,
diamond?
so, few extra parts to this. Okay, so step one, still the same. Which one goes in the middle?
Gross.
Bromine, because there's one. Because yeah, you go off the single rule first, and then the electronegativity rule. Good point, though. Okay, so Br is gonna go in the middle, and then I have 1, 2, 3. Oxygen is bonding to.
That's what you think.
Okay. Step 2, place valence electrons. So oxygen comes to the party with 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Can people in the back, can you see if I just do a dot with my marker? Or do I need to make them bigger?
Yeah, no.
How's it look on the camera? Is it?
You can see it.
You can see it. Okay, and then bromine comes to the party with 7.
I know. Yeah, we should.
I don't know if we can.
5, 6.
Try. No, that's like slightly better.
This looks like a mess. Oh dear.
Okay. Now, I know it looks better on your paper, not my paper. So first
Yeah,
one
you can
is
see-
the
you can see
charge.
the dot.
Look on your paper, and it has our bromine has a -1 charge, or the molecule has a -1 charge attached to that. Everybody circle that charge,
I'm sure it's one
BR has
okay? And make a note, okay? Circle that negative. What does a negative charge mean about an atom?
There's an extra
What
electron.
if
We
we?
have an extra electron to place somewhere. Okay? So this is kind of a side step if necessary. Right? Like if you have a negative charge, or what if I had a positive charge? Then you need to
That's
take
like
an
okay, you
electron
can
away.
do
Okay? I always add extra to an outside atom.
Yeah.
Doesn't really matter because you'll see in the end like it works itself out. So in this case we have 1 electron. I'm going to do it orange just to show you. So I'm going to add that 1 electron just to this oxygen. You could have placed it somewhere else, but don't forget about adding extra if there are negative charges. Okay, so if you want to make a little side note on placing valence electrons, is make sure you pay attention to charge. Okay, step 3 is the same though. We now are going to bond to complete the octets for the outside atoms. Okay, so oxygen comes with 6, so it needs to bond
Twice.
2
Double
more
bond.
times. So 1,
Double bond.
2. Okay, I'm gonna move one of my dots over here just because of how I drew it. Okay, so this side is also gonna bond. 1, 2. Now this side, how many times does it need to bond? Just once, because I gave it the bonus. Okay. Yeah, Jess.
Wait, I thought a line meant like it had 2. Does that mean like, is it because there's 2 like things, so what each element is 1? That was a 2.
So it's like they like both put them in the middle, and now it belongs to both. So a line does count as 2, so that's why we always connect 2 dots to make a line. Does that answer your question? Sophia.
See, but now bromine is unhappy.
So that's your question.
The oxygens.
It has so many.
Okay, back up for a second here. So let's check our oxygens real quick. So thumbs up, thumbs down. Is he happy? And don't tell me 6.
They're just.
Okay, happy?
Yeah.
Happy?
You hear that? D6. You
Now, let's go back to what Sophia brought up.
No.
He's
He's got A's.
10, 11,
Oh.
13.
What?
It's like getting extra.
What you, for those that have taken chemistry before, ever drawn these in other science classes, atoms can bond past 8. Octet is it's like, that's what they generally want, but there's a possibility to bond past it, and it doesn't make them unhappy. Now we'll talk about, there's some elements that can never do it. Like, they would be very unhappy if you tried to make them bond past 8. But elements that have the D shell are capable of expanding their octet past 8 and still be considered stable and full.
Because bromine has.
Wait, so what if bromine was like chlorine? Would it not be happy?
Oh.
So, good point. So everyone look over here with what Aiden brought up. Okay, so bromine is here, right? Now what's interesting is you gotta go to the numbers of the D shell. What number is this shell? 3. So even though these don't have electrons in the D, they still can expand into it. So it's only the second row because there's no such thing as a 2D orbital. These ones can never go past 8, ever. But everything else can. So chlorine can, and I'll show you, let me draw a picture. It can shift its electrons in. The next problem we do, Aiden, it'll make more sense because it is one from, it's sulfur that we're going to draw next. But questions on that for now? Grant?
Why is the bromine blue?
Because it's a liquid at room temperature.
Wait,
Yeah,
bromine
there's
is also
Wait, why is gallium not blue then?
Oh, mercury.
Is that
it's not a
room
room
temperature? It's not?
It's like 20
It's like
degrees
just
colder
barely
than
above,
Because room temperature is a standard 23 degrees Celsius.
Wait, but then why is bromine one of those ones that's
Rum.
What do you mean, like? Like where to put your dots?
That's not what we want.
Once again, it doesn't really matter, and that's where, like, lots of times after I draw my picture, if it doesn't look as clean, like my lines are kind of stretched, I would just redraw it a little bit, like this. It's hard to kind of say a hard rule out of them, but the more you draw these, you'll just kind of start learning the best place to put them. But there's not like a rule, like always put them here, always put them here.
So I figured out.
But you'll just get better at like, but if you have to like stretch your lines in the beginning, just like, and then redraw it to make it clean, that's not fine. Does that kind of help?
Camera. I can change the
Okay, now,
I can change the roll.
few notes on this, and then we'll answer your question, Sophia. So when you do have a charge, so this is kind of like an extra rule, your Lewis structure does need to reflect the charge of it. So we put brackets around it, and you put the charge outside. You need to indicate to someone else who's looking at your picture why there's an extra electron there that technically wasn't. So, Sophia, what was your question?
Wait, so if you like have chlorine instead of bromine, or like silver?
It would, yep.
But then if you had fluorine, but
Fluorine would never, yep. Okay, questions so far? Okay, let's do, everybody flip your paper. So turn it 2 pages over and there's a blank piece of paper. We're gonna do some practice problems right now. Everybody find that?
Okay.
Don't make me.
Since you haven't gotten enough, for some more smiley faces. That's the end of term or something.
I don't smiley faces. Yeah.
Okay, I'm gonna give you 3 structures. You're gonna draw their pictures on.
Do it? Okay.
So draw me a picture of this. Let's draw.
H3.
Oh wait,
Okay, ready, set, go. With your table, buddy, draw me 3 pictures on your paper.
Or does that mean you only have
What's going on?
Oh, but bromine isn't as
But it gets certain electrons.
How does S have? S has 5, 1, 2.
Oh, there's one more. Ladies and gentlemen. Wait a second. Wait a second.
Say what?
What is it? Neon.
You can, but they don't count.
Oh, not neon.
Just on the grade.
Oh, so if you have like 9
Does it go
Wait, no. S has how many? And then we add 2 more. Whoa. So wait, they can have up to 10.
Oh, there's 4. That's awesome.
2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14, 16.
Oh, wait. I forgot. Because, look.
Yeah, it's 2 minus. So you add the 2 extra to the S, and then it has 2 on each side, and you can make 2 double, you can make a double bond.
Always add extra to the outside atoms. Because the central will always get more than what it needs.
Oh, wait, so you already do the X bonding.
Yeah, always add extra electrons to outside atoms, not the central. Because the central already gets filled up.
Wait, no, it doesn't work then. Oh, wait, yeah, it does. So you add an extra one to that, and add an extra one to that, yep. And then you do 2 minus. That does look correct.
All around the C,
Wait, what?
Because the middle one can go past 8, but if it like doesn't need to, like it won't.
Wait a second. How with a xenon bond?
That's what I'm saying.
Wait a second. Whoa.
It also kind of goes with the idea of like electronegativity, right? That the outside ones have higher electronegativity, so they're more likely to grab extra electrons that are out there.
So when xenon's still bonded,
Yep, so this is the case because things can go past 8. Some of the bigger noble gases actually do bond.
But not of their own accord, because they don't want to.
No, but if they're with something like chlorine that's really reactive, right? They can kind of, I guess I'll bond.
Maybe with Carl Lewis.
But he's not sitting here.
I hope the camera picked that up. Okay, so look, if I adjust this knob, that doesn't move, but I can do this. And that's really unhelpful.
Okay, looks like we're almost there.
Watch, he's like, it's a trick question. It doesn't bond. This doesn't exist. It's like, oh, dang it. Why would it? Exactly. She's like, it's a trick question. It doesn't bond.
Porter Logan.
No way.
Yeah. She was in love with Jake.
And then go past the test.
That's a trick question, actually.
She's in love with
It's
Porter.
that dividing line. That things of stuff that will never go past.
I don't know. Remember when I was in love with
If
him?
they were to show
That
you a
was bad
molecule
time
or a
in my
line,
life.
you should be able to say like that does not exist.
Are you in love with him?
No.
Do you
Does that
think
make
he's...
sense?
Yeah.
Yeah.
We were just talking about that and how you wear skinny jeans.
Oh, he has the same khaki pants.
Okay.
I know someone else who's.
Let's check. If your answer is the same as mine, you can have a smiley face for it. If it's not the same and you want me to walk through it piece by piece, let me know. But I walked around and it looks like we're doing pretty good. So, okay, on this one you should have though something like this.
Okay, alright, looks good.
That's a smiley.
Questions on that structure?
Okay.
Okay, this one you should have something like this.
Me when my lips are crooked.
Me when my lips are One, two, three, four.
Questions on this one?
That's what we did.
Yeah, my love.
On the sides of the oxygens with only, if only the six.
Wait, does it matter if it's
You'll find if you
rotate it.
separate
Okay.
one of the, I guess, yeah, no.
You got it, big. Okay. Any other questions on this one?
but like this hand here, bro?
Good. Once again, you make sure you do have those brackets on there. That is part of like
Okay, so
the correct structure.
orange.
Okay, and then this one you should have.
Why?
And then you should have, wherever you put them, but 2 extra sets of lone pairs that didn't bond with anything.
But why?
So 3 smiley faces together. Yeah, Ashton.
Why would it bond though? Because it has a full shell.
So, because of that expand, let me show you this actually, this will kind of link into it. So, going back to what you asked Eden. So, sulfur, right, normally, okay, so everybody, this is how the expanded octets work when they can go past 8. Okay, so sulfur, this is its normal ground state valence shell electron configuration, right? It has 2 in the S and 4 in the E. Okay? When things bond, okay, give me your attention here, everybody. Electrons can be excited and move to higher different orbitals in order to make the bonding happen. Or like, a lot of times in order to make a reaction happen, energy is put into it anyways. Like, you heat something up to make it react, or you light it on fire to make it react, right? Or even just stirring it, right, can help create energy to make things react. So what happens to explain how sulfur can bond 6 times is there's the D shell is available. It's empty, but it is available for space. So what sulfur does, or how we explain this, is it shifts, okay, one of each of those electrons up, because in order to bond, you have to have a half empty shell, because the shear has to come from somewhere else. So now you have 1, 2, 3, 4, 5, 6 bonding sites. 1, 2, 3, 4, 5, 6. So that's why even though the D isn't filled, it can jump into it to fill it up. This is why, once again, make a big note to yourself that like oxygen, nitrogen, fluorine, and carbon, and neon, like those ones, will never ever go past 8 because they have nowhere to go. They don't exist. Right? Anything past 8 for those is not a real molecule. Just because you can draw it on paper doesn't make it real. So, Trevor and Joel.
Can't bond with anything then?
So neon, yeah, so neon and helium are the 2 atoms that never form any bonds ever. So, and then kind of going back to this one, so that's how the expanded octet works. And then what happens is if a noble gas comes in contact with something that is very reactive, like fluorine, it will bond with it at times, even though, because it's still stable, so we didn't really change its stability. But if the thing that's coming at it is like, I mean, fluorine is very electronegative, right? So it's really gonna be like, well, I really want your electrons, right? And so it just doesn't, they still are willing to share it. Once again, not common, like noble gases don't commonly bond with things, but it can be done under certain situations.
Fluorine most likely to nuclear atom.
Yep. It's the toughest one of all, always wins the tug of war, so.
Could you be able to like make it so that way it's Ne plus, so that way it didn't bond? Or would it
I
then
don't
just
know.
steal an electron from the other atom so that way it's happy again?
I don't know, I mean, cause any plus would mean you're forcing an electron upon it, right? Or you wanna make it,
No, you're stealing an
I mean, you wanna
electron.
take one away? I mean, theoretically, yes, in a lab setting, but its ionization energy would be like crazy high to do that, right? So, I don't know what would happen though, Milo, that's a good question. From what I know, from what I've researched, is they've never made a stable compound with neon, so if they've tried that, I don't know what happens. Like, or if they just can't get enough energy
So
to
it's
throw it off.
they might have made one, but it's unstable.
But maybe it just like breaks back apart, right? So,
The neon is just like, okay, no, this is
like,
actually
no,
mine.
I really don't want to be with you, see ya. So, Joel,
Aren't all of those, are those not happy?
are they not happy? Who's not happy?
I see those smiley faces.
Oh.
I'm just
That's
kidding.
weird.
Tricky guy.
We got 3 for getting them right.
Yeah,
So.
that's great.
They can't be happy if they don't see that smiley face. Okay, now let's add a few. So that's the main thing is Lewis structure. So 2.5 is just a bunch of Lewis structure practice. Now there's just some side things with Lewis structures we need to take note of. The first one is this thing known as a formal charge. Okay, formal charge is a way in which you can check the legitimacy of a structure. So if you were given, which I'll show you here is an example, or you find yourself like, wait, I could draw this multiple ways and everybody's still happy. Formal charge is a way in which you can check to see what's the actual way the structure truly is. So for example, this is on your paper. Which one's first? Double bond or single bond? Carbon dioxide, isn't that right below it?
Yeah.
Okay, so you could draw carbon dioxide like this, and everybody's happy, 888. Or you could draw carbon dioxide like this, and technically everybody still has 8. Okay. Random dot. Okay, so they can be drawn either way, and people could argue saying like, oh, well, they both have 8, so how do we know what the true structure is? The nice thing is, and the reason why I teach drawing the way I just taught you, is if you follow that system we just did, you'll always end up with the right structure. Because it just goes the way it has to go. But a lot of times what AP people like to do is they'll show you various structures and you need to pick between them, and so you use formal charges to check it. The equation for formal charge is we take the number of valence electrons, okay? And then this is, I'm gonna write down, this is like the official equation, and then I'll show you how I interpret it. Then you're gonna do minus 1/2 the electrons in bonds, minus what are called the lone pairs, meaning the electrons not in a bond. If you do want to make a little side note to yourself, this equation is not on your formula sheet. Sorry, I didn't make it for the sheet. For some reason, they felt like you could memorize it and you'd have to have it written down. So, now, the simplified way I look at this equation, so this is my interpretation, is I say we need valence electrons, so VE, minus lines, minus dots. That's how I think of the equation, because that's pretty much what we're doing. Now keep in mind, formal charge is for individual atoms. We can add them up in the end, but you calculate it individually for each piece. I see a hand in the back. Okay. All right, so let's test it for this. Okay, so oxygen has how many valence electrons?
6.
6. Okay, I'm going to minus the lines. There's 2 of those. I'm going to minus the dots. There's 4 of those. So this oxygen has a formal charge of 0. 0 is the goal. 0 means it is a stable bonding arrangement. Okay, carbon has how many valence electrons? 4.
4.
I'm going to minus 4 lines. It has 0 dots on it. So it also has a formal charge of 0. Okay, let's do the last oxygen. It's symmetrical, so it's the same, but just to check it. Also at 0. This tells me, without even checking the other structure, that this is the true structure of carbon dioxide. It's the most stable arrangement for it to be in. To compare, if we were to do the formal charges for this, once again, oxygen has 6, but now I'm minusing 3 lines and 2 dots.
Oh.
So plus 1. The carbon ends up being 0. But then this option ends up being minus 1. So even though the overall charge is 0, the individual ones are not balanced like they should be. So
It's just so surprising.
questions on calculating a formal charge? Now, with the formal charge, sometimes you can't get it to be 0 all across. Just a lot of times if the molecule is charged, it won't be, because the molecule has a charge attached to it. So if you need to determine which one is the best choice between a charge, it goes back to electronegativity. The more electronegative atom can stabilize that negative charge. So that's where you want the negative formal charge to be. So the more electronegative element should have negative charge if it can't be 0. Okay, once again, if it can't be 0, then you put it on the more electronegative atom. So, question, Sam?
So in the homework, there's CO, and it seems like it shouldn't work because then the oxygen would be happy, but the carbon would only have 6. But
Hold that for a moment and we'll address it. But yes, there's some weird things that can happen sometimes. Okay, so try this practice problem with your table buddy. So between A, B, or C, using formal charges, which structure is the most likely correct? What?
Alright, who's our most electronegative opponent?
okay, wait, let's see. Oh yeah.
That's a 6. This is gonna be 0, this is gonna be 0. N is 5. So N is now negative 1.
So there should always.
I don't know if that's true actually. Yeah.
Because
No, which one? Yeah, we'll look at N.
This one has 6.
N has 5.
Wait, that's not. Oh, well, no, because it's a
The
negative.
minus. Yeah. Which one is more electronegative? I think it would be nitrogen is more electronegative, right? Right? Okay, so let's just say it's probably not this one, but 1 and -2. So that's kind of stupid. So,
Wait, is it saying which one's more stable?
yeah, which one is more stable? Or the domino. So, not that big. So I'm thinking nitrogen would have a higher electronegativity to sulfur because it's an energy level down. So I'd say B. So then it gets the extra. Oh, rapid storm.
You don't really pull charge. Don't think about the charge you get to relationship. The formal charge should add up to what the charge is.
I don't know if I can for sure do it because my dad wants to do it with me. My dad wants to watch it because
You should help me with that.
he has a chemistry major and he wants me to.
That's our default charge. So in this case, it's 0, 0, minus 1.
I know, he's not even a chemist. So like, I
This extra like thing is like
you can
No magnetic storm.
That's right.
But they are very similar, like they're almost the same. Okay. Okay, if you selected answer B, you have smileys. Okay. So what you should have brought in for formal charges is this. This is really weird, like,
Wait, which one's more electronegative though?
okay, so first off, hopefully no one picks C, because those numbers are just way off, right? So then, they're very similar, but now it's just a matter of which one is more electronegative, and maybe some of you just got to that point and then just picked the wrong one. So nitrogen has a higher electronegativity than sulfur, and once again, they are very debatable because they're close, but up and down has a greater effect on the trends than left to right does. And so nitrogen is higher in electronegativity, so the negative will dwell on it. It's also why the extra electron was given to the nitrogen in balancing it out. But
Would they try to trick us by like putting electrons diagonally?
I don't know why they did that. I just found this question. It does look weird though, huh? Like, why did they do that? They didn't do it on each other.
Well, it's because the other ones didn't have
I
like
guess they
different
couldn't, so.
things.
So,
That one had.
questions on formal charges though?
So regarding like the electronegativity, are you like doing it off which one has the -1? So it's like sulfur compared to
So it's the trend that goes from bottom left to top right. It increases as you go that way. Yeah, so I'm just comparing the sulfur to the nitrogen. So because they're both like pretty much the same except for where the nitrogen is. Does that make sense? Okay. All right, Sam, this is going to answer your question. Okay, everybody.
Yes.
Now, let's draw a picture here and explain some interesting things that can happen within an atom as known as resonance. Okay? So we're going to draw a picture of a structure of ozone, which is 3 oxygens bonded together. Okay?
Frozone.
Where's my super?
Okay, how many does oxygen come to the morning with? 6, so give them all 6. 1, 2, 3, 4,
Bro, she's
5, 6.
She's doing the homework for you.
1, 2, 3, 4, 5, 6.
What is this?
Okay. Now, one thing you need to understand with Lewis structures in chemistry, right, is sometimes scientists know that certain things exist. Like, we know ozone exists, we know it's O3. And so then the Lewis structure is scientists have to figure out, okay, well, how could this structure work? Like, you have to explain because we know it bonds. Okay? So, in the study of that, there are some interesting things they can find. Okay, now first off, bond them once, right? We know it's a structure, so we know there's a bond somewhere on both sides. Okay? But it gets problematic. Why?
Because
Overflow.
So oxygen, remember that there, oxygen can't go past 8.
Yeah. So you turn it into a triangle.
Not a bad thought. Triangle bonds are really, 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 really difficult because of how close it brings them together. Even square bonds are pretty rare. That's why we see a lot of pentagons and hexagons. But not a bad thought, Milo. So, in studying ozone, scientists found out an interesting thing. Okay? Scientists found that the length of the bond in ozone was longer than a single bond, but shorter than a double bond.
What?
This is 1.5 bond.
It's like a half bond.
So that's kind of what it appears to be is this idea of
Great, so now they can just bond however they
But
want.
longer, wait, you said longer than a single bond?
I mean,
so
it's only
short. Did I say that backwards? Shorter than a single. So I'll show you a picture here. Okay, so here's the data that they found. Okay, they found that a double bond had this length, a single bond had that length. But the actual structure of ozone was right in, was somewhat in between both of them.
I love it.
So, what scientists are saying is happening here, this once again will only happen with the elements that can't, so, okay. The first thing I'm going to show you only happens with like oxygen and nitrogen, the ones that can't go past 8. Where the way scientists explain it is they say, well, electrons are very mobile things. And so we have this concept of resonating where electrons, if needs be, must be able to transfer completely from one element to another. So in order to make this thing satisfied, okay, one of these electrons, okay, gets transferred over, because then I now have space. Oh, here we go. I just move my dots around a bit
That makes sense.
to double bond on the other side.
Oh.
Because now everybody has 8, 8, and 8. Now that's not the final answer though, because what they found in the study was it's not one side is shorter and the other side is longer. They found it was equally divided. So really what's happening is, using the word resonating, is the molecule is in constant movement between these two structures. Go ahead, Grant.
Oh yeah, so you mean it's shorter than a single bond and longer than a double
Yes,
bond?
thank you. I said that backwards.
Okay, because yeah.
Yeah, so shorter than single, longer than double. So what they found is ozone is not this. Ozone is not this.
It's both.
Ozone is a constant blend of both.
Does that make unstable
I
now?
don't like that. Nothing, this is not.
I mean, ozone is unstable. I don't know, because resonance doesn't always, resonance actually makes things more stable because of the movement, but it does change some interesting things. The way I visualize resonance, everybody, is think of it like a fan in motion, okay? When a ceiling fan is stopped, you can see, right, the 4 different blades or however many blades are on it. But when the fan is turned on, it appears as if it's everywhere. And that's kind of the same idea with the electrons.
Okay.
The electrons aren't here or there, they appear to be filling the entire, both sides of it at once. So yeah, it's kind of like a 1.5 bond, but it's not 1.5 in that everybody has 8 still, right? All atoms still have their stability.
So if we got this question on like a test or something, would we have to write both?
Yes, so the correct answer for a resonance structure is both pictures with this arrow in between. This is known as the resonance arrow. Okay? So the way to check for resonance, if you want to make a note, is when you have double bonds, check to see if it's possible to draw mirror images of your structure. If you can draw mirror images but they're technically different, then the molecule would resonate between those different images. So going back to the one we did as a practice problem, this one, right? This is actually a resonance structure. Because you could draw the double bonds here, you could draw them there, you could also draw them like here or there, and so it actually can resonate in a lot of different ways. Now on your homework, I'm going to give you approval because I only gave you tiny boxes for drawing, that if you identify that something resonates, then underneath your picture just draw the arrow to tell me, hey, I know this resonates, but you don't have to draw like all the variations. But like on the AP test, you do have to draw the variations of resonance. So that's my
So with that one, would you draw arrows in between like 7 different ways that it could be?
technically,
Like,
yeah. Because there's, what, 6 different structures it could do?
Yeah, yeah. 1, 2, 3. So I guess 1, 2, 3.
6.
5, 6, 7.
Yeah, so technically, yeah. So, other questions on what resonance is or how to identify if something resonates? Once again, just to kind of show you another one, just in a fun to show, molecules can form hexagonal shapes or pentagonal shapes. It's not so much something you'll draw in this class, but just to show you like they are a thing, right? Like dopamine. Like dopamine has a hexagon that resonates with double bonds. So kind of cool. This is when you get into, if you ever take organic chemistry in college, super cool Lewis structures. This, everybody, in organic chemistry language, would look like this.
That's just sugar, isn't it? No, it's not. What?
So this is that to an organic chemist. The sun. So in organic chemistry, Lewis structures get simplified because they get more complicated. In that carbon, you don't draw, so you don't ever write carbon in organic because carbon is the backbone of everything organic. So everywhere two lines intersect, that means there's a carbon there. And then you drop all hydrogens, but someone reading it just assumes the missing spots are hydrogens to get to 8. So, anyways, you don't have to worry about drawing that way, but just kind of cool to see like what Lewis structures can eventually turn into. So, like our dopamine over there in Lewis structure terms would look like this.
Oh yeah, the carbon. That's like inside.
Oh, it's almost.
Well, you took it.
So that is that. Just kind of cool to see where it's going. Okay, now last thing we're going to talk about are just a few type of exceptions that can happen. Once again, make a big note, they are exceptions. So try to do everything you can to not let these things happen. But sometimes you can do everything you want to and it just happens. For example, you can end up with an odd number of electrons. For example, let's draw a picture of no. Right, so nitrogen comes with 5. 1, 2, 3, 4, 5.
Let's do something.
Oxygen comes with 6.
I thought that's a no.
Okay. So, bond to try to get them full. So oxygen needs how many more electrons?
2.
2, so I can bond twice. But can oxygen bond anymore? No. And so you're just done.
What?
Because there's nothing else you, sorry. There's nothing, we can't, like, you're just stuck. So that's just what it is. That there is a way to do it. Now with this once again, it's just an exception. Molecules with an odd number of electrons for those that have taken, maybe talk about biology. Take biochem, definitely will. But if you've ever heard of a free radical before, ever heard of that?
Exactly.
Like in terms of food?
Why doesn't that?
Or like how certain things give you free radicals and it's not good, so that's why you eat blueberries and antioxidants. So anyways, odd numbered things are known as free radicals because they're super reactive, right? So. Okay, another type of exception, everybody, is sometimes you have less than an octet. So we talked about how you can have more, but sometimes you might be short. Bromine is really where it's going to happen because how many electrons does bromine come with?
3.
Only 3.
Isn't that boron?
What did I say? Bromine. I meant boron. Why are y'all looking at me? So, if you think through it, right, if bromine only comes with 3, it's impossible for it to do anything but this. And it's just the way it is.
Well, I guess then it's S orbital is empty, so it's kind of happy.
And that's kind of how, if you think about it, right, and that's how they explain it, is like, well, its P shell would now be filled because it would shift it up, and so it is stable to some extent. So, and then finally, we already mentioned it, but more than an octet, and this can also mean you can bond with more than just 4 things. So, phosphorus pentafluoride is a molecule.
Whoa, that sounds kind of.
That's my favorite big.
Okay, so phosphorus is in the middle. How many valence electrons does phosphorus have? 5, which you can kind of see there's 5 fluorine, so it's going to bond.
So then you draw
Like this.
Yep, so you start turning them into like little stars when you have to do more than 4.
That's so cool.
And then obviously these all have their lone pairs on it. But once again, like we mentioned, only if they have a third shell can they do this. Right? So like nitrogen, oxygen, fluorine can never ever do an expanded octet. It doesn't exist. So this guy.
Away.
Has to expand.
Still by like just like
Have you ever tried to?
It is, so this would be like the case of it is pulling, but they are still shielded.
Lithium, beryllium, boron.
Yeah, so even though you can draw nitrogen with 5 things around it, it just doesn't happen. It doesn't have that Okay, any last minute questions? You're like, wow. Must be a sign.
Spelled like that.
Oh, it's C-L-O. Not C-I.
The non-gal 6 bar.
Session.
I don't even know where to go, bro.
Okay, few notes here, everybody.
I don't want to
Okay, give me your attention. Alright, we got 4 minutes left. In this class, we continue to be productive until 1 minute left. So everyone should pull out this homework and at least do one of them before the bell rings. Okay? Now, just a few typos. If you didn't hear, the second one is C-L-O-3, not C-I-O-3.
See, I thought that.
Okay? And then I would put a little star by N2O. Be careful with that one because it can't do an expanded octet. So be careful. And then same thing, there's a nitrogen one on the back to be extra careful with too. So, okay, work for the next 3 minutes. I'll come around and answer any other low questions you might have.
Oh.